The last method I'm going to show for special right triangles is going back to the basics, which is that you're dealing with squares and equilateral triangles. A square has the 45, 45, 90, because when you split a square right in half, it gives you those two 45 angles. And same with the equilateral triangle. When we split the equilateral triangle in half, it gives us that little right angle with the 60 and 30. So we're going to look at another method of how to solve these problems using that same idea. So I see that I've got these two angles the same measure, which means that I can then create a square out of it. So that means that this 10 is the same as this down here. And then I can use Pythagorean theorem. So adding around the right angle, I've got 10 squared plus 10 squared equals x squared. And so 10 squared is 100 plus 10 squared is 100 equals x squared. So that'll be 200 is x squared. Then you have to do the tree method though, because we've got the square root of not 100, of 200 equal to x. And therefore, when you finish, you'll get 10 root 2 for x once you've done the tree on that. This last one, or that's not this last one, this next one is the same idea, right? We've got the 45-degree angle, which means this is also 45, which means that we're dealing with, again, a square. So these two sides are equal. So if that's an x, this is also an x. So we can do the same thing, Pythagorean theorem. X squared plus x squared equals 15 squared. This becomes 2x squared equal to 225. It gets a little messy here though if you're using this method, just as a heads up, but you're going to end up with 225. Oops, sorry, not 4. I would not write it as a decimal because we do want our answers as simplified radicals. So I mentioned that up here. So this is 225 over 2. So x squared is equal to the square root of 225 divided by the square root of 2. The square root of 225 is pretty nice because that's just 15. And then we need to rationalize the denominator. So we'll copy, paste, and delete. So we'll multiply both numerator and denominator by root 2. So this is going to get me 15 root 2 over 2. That's my final answer. So that means that x is 15 root 2 over 2. The 30, 60, 90. So this is where you need to remember that previously I showed if you have an equilateral triangle, you bring it down the center. This is your 60, that's your 30. And all of the sides were equal, but when you split it down the middle, now these two are equal. So if I were to recreate the 30, 60, 90, that 30 degrees is reflecting over. So it's the 30 degrees reflecting over, which means that my triangle will kind of extend down this way. Let me see if I can make that look a little neater. All right, so now we've got our equilateral triangle. So if this is x and that is x, then this whole length is x. And I see that it's splitting the bottom into two equal parts. So this side and this side are equal. So that means this is also 12. So 12 plus 12 will give me my x. So my x is 24. And then I can use Pythagorean theorem, adding around the right angle to solve for y. So I've got y squared plus 12 squared equals, equals 24 squared. And I'm going to pause so I can get my calculator. Okay, so 12 squared I already knew was 144. But 294 squared is 576. So subtracting 144 from both sides, I get y squared is equal to 432. And then I can split this one up because y squared will be the square root of 432. And hopefully we end up with I'm looking at the wrong one, 12 root 3. So let's see if we do. So I'm going to get 2 times 216, 2 times 108, 2 times 54, 2 times 27, 3 times 9, 3 times 3. So couples are going out. 1, 2, 3 of them. So that's a 2. times 2 times 3, and then single stay in. Looks good. So this is my y, so y is 12 root 3. And then again, when you're looking at reflecting it over the 30 degrees, so not the 60 over the 30. And so then we're going to end up with saying that this is the same as this, which is the same as this whole length. So this whole length is 16, which means that y is half of it. Y is just 8. And then we can do 8 squared plus x squared. So 8 squared plus x squared is equal to 16 squared. 64 plus x squared is, I believe, is 256, but I'll double check. Yep. Subtract 64 x squared is 256 minus 64 is 192. And hopefully we're going to get 8 for, no, not 8 for x, sorry, 8 root 3, 8 root 3. So let's see. So when we do the square root, right, x squared is equal to x is equal to the square root of 192. 2 and, nope, that's going to be 96. 2 and 48. 2 and 24. 2 and 12. 2 and 6. So 1, 2 2s. Oh, sorry, just kidding. 2 and 3. Almost missed those ones. 3 2s. So that's 2 times 2 times 2, and then that lonely 3 is left inside, so root 3. So x is 8 root 3 when we simplify that down. That goes up to there. And then this is a square, so we can bring that 6 over. And once again, I want to go poop, drop this out. So this is kind of a funky one, but this is x, and this is x. So what I would do is I would see that x is the same as y plus y. So x is the same as 2y. And then I'd bring that 2y up here instead of the x. So I would use the 2y, y, and 6 when solving this one. So I'm adding around the right angle. I'm doing 6 squared plus y squared equals 2y squared. So 36 plus y squared equals 4y squared. I'm going to subtract y squared from both sides. And I get 36 is equal to 3y squared. I'm going to divide by 3 and get y squared is equal to 12. The square root of 12 simplifies down to 2 root 3 for y. And then this one looks like I need to solve for two sides. So I'm going to solve for this y first because it's on my shared side. So I've got the square going down here, which means that all of these side lengths are equal. So deleting all that now. I've got the 6 over here, so going around the right angle. I've got 6 squared plus 6 squared equals y squared. 36 plus 36 equals y squared. 72 is y squared. So square root of 72 is equal to y, which simplifies down to 6 root 2 for y. So this is 6 root 2. Now I can reflect this over the 30, and that'll get me the fact that this is, if I make this z now, it's because that'll be z plus z to get me 2z. So I'll have 2z, z, and 6 root 2. So this will be z squared plus 6 root 2 squared equals 2z squared. So we'll have z squared plus, and I would write this out as 6 root 2 times 6 root 2 equal to 4z squared. I'll subtract the z squared and simplify. So this will be 3 z squared is equal to, this will combine 36 root 4 is 72. Divide by 3 is going to leave me with 24 equal to z, root 24. Well, 24 equal to z squared. I'm going very fast, aren't I? Square root of 24 is z. So then it'll simplify down to 2 root 6 for z. So z is 2 root 6, but 2 times 2 root 6 will give me the x value, which is what I'm looking for. So that'll be 4 root 6 for the x. So same idea, same idea. We've already got the x. We're trying to find the x up there. So let me erase that little thing so we can see the x. So I'm going to have x, y, and z. So hopefully that'll all work out. So these are all squares because this is equal to each other. All of these angles are equal, so they're all 45s. So that means that this is the square that I'm dealing with. All 4 sides are equal. So let's get that 3 on the other side and do Pythagorean theorem. So this is a 3. So 3 squared plus 3 squared equals z squared. 9 plus 9 equals z squared. 18 equals z squared. So root 18 is z, and that simplifies to 3 root 2. So this is 3 root 2. And again, looking at the second triangle, so here I'll just do it like that. We've got this little square right here. So now I can take these 2 sides, which are equal to each other. So this will also be 3 root 2. And multiply those all out to get the y value. So 3 root 2 squared plus 3 root 2 squared is equal to y squared. So 3 root 2 squared is the same as 3 squared root 2 squared and 3 squared root 2 squared. When you square root, it cancels it out. So we'll have 9 times 2, 9 times 2. So that's 18 and 18. So that'll be, let's see, 36. And taking the square root of 36. So that'll be just 6. So this is 6, which is awesome because now, we've got a square. We just want to know what this x is. Well, that's the same as that, which was 6. So that's how you tackle it with the visual method of identifying them as equilateral triangles and squares.